Mario, Mario, Mario. Thank you, that was my voice stem overflowed from Mario-san. Welcome back to Devlog. In the last part, I work on a 3D movement controller for a fast-paced robotic controller without the use of physics. This video is very long and extensive in how I designed and made the system, so there are timestamps in the description for each individual section in case you want to skip to maybe a part where one aspect is explained and you do not care for other parts, because you don't feel like watching a 50-minute video on flying movements. I better not see my viewer retention go bad because you didn't click the numbers. My main inspiration for this controller was because I really wanted to just make a fast movement controller. I find the idea of moving incredibly quickly in a game both fascinating to code for and fascinating to play for. The reason I wanted to code this is because I think moving at extreme speeds has a lot of issues with collision geometry and also traversing geometry, and I wanted to try to remedy these solutions in a coding system. And also, I like speed lines when you go real quick. In fact, one of the main inspirations for this controller is the speed you can get in the game Gravity Rush when falling. The pure act of falling in that game I find to be incredibly satisfying just because it feels very fast for the player. So I wanted to maybe try to replicate some of that feeling in speed, but also make a controller where all of your movements can be extensively fast. And also, the first thing I had to do was create the way momentum and the motor would work. Regardless of any physics, regardless of any movements, the initial thing I had to do is work on the momentum system for how the character actually traverses through the area. The way I do this is by using a transform translate function and deriving a lot of information from recasts, sphere casts, and another one that I've forgotten the name of, to tell what the geometry of an area is when the player is moving. This is actually very similar to how I coded the movement in Pal, a funny 2D game, but translating this to a 3D geometry is a bit trickier. Essentially in Pal, I have momentum as a 1 float. This is just a value from 0 to 1 or -1 for if the player's momentum is going left or right. So at -1 she would move left, at 1 she would move right, at 0 she wouldn't move, etc, etc, and this would all be relative to the ground. The issue with this is that in 3D there is a three-dimensional axis to move on and not a two-dimensional axis to move on like in a 2D game. So I had to translate this movement mechanic that I had made for Pal into a 3D environment. The way I did this is by translating movement to a vector 2. So momentum is contained in a vector 2 array. These are two values, x and y, x being how much the character is moving forward, y being how much the character is moving right. So if I were to press right on the joystick, this value would move on x value to 0, y value to 1 because we are moving to the right. If this value was 1, 1, we would move forward and right, so diagonally. Very simple, just a vector 2. But what I have to do is now translate this to player movement in-game. Right now you're probably thinking, why use a vector 2 array when the game is three-dimensional? You should probably use a vector 3 array because this can just get the direction you are supposed to be moving in world space, and you don't need to translate this to a vector 2. The reason I didn't use a vector 3 array is because they are difficult to adjust for, and the way I code movement is not actually three-dimensional. It is technically two-dimensional because I register any surface the player is standing on as a flat object and simply move them around this as if it is a flat object. How does this work, you may ask? I will tell you. So the way the vector 2 array works in movement is that I use a variety of recasts, a variety of collision detections when the player is on flat ground. When the player is in the air, none of this is needed because in-air movement is very simple. But when the player is on the ground, I detect what the ground surface is. Let's say it is a flat plane. All I do for this is then move the player either forwards, backwards, left, and right relative to the vector 2 array. So are two values, and then I move them in the direction of the actual fluid geometry and not a world space geometry. I completely ignore any world space geometry. I move the character relative to whatever they are stood on and whatever the angles of this surface are. So, for example, a flat plane, we're going to be moving forward on the flat plane if we press forward. If the plane is rotated 45 degrees, so it is tilting upwards, we are going to still be moving forward relative to our vector array, but now in world space we're moving upwards and forwards because we are moving both forwards and upwards due to the tilting of the plane that we are stood on. The reason for this is mostly because at very high speeds I find using a vector-free array that is the direction of movement can lead to things where the player is incorrectly overshooting platforms that they are running on. Let's say a tilted block, if they reach the top of it but it is tilted, they will still overshoot this because they built way too much speed, or they will fall off a slope when going forwards because they are moving too fast and they completely overshoot the ground geometry that they are currently on. This way, at very, very high speeds, the player is probably not going to overshoot any geometry because the player is moving on the geometry relative to the ground angles. The player can still overshoot some geometry, but this is a deliberate coding system that I will discuss later. And by later, I mean probably right now. One issue you may be thinking is, if all movement is on a vector 2 where you are registering any ground geometry as a flat plane, how does the player fall off any geometry? And I'll tell you in a complicated way. In this demo footage I have a lot of cubes that are tilted. Now the cubes are tilted in a way where the actual angle between one side of the cube and another side of the cube is 90 degrees, as all cubes are. So, if the player is running up one side of the cube and they get to the top of the cube, ideally, I would prefer for them not to overshoot the actual geometry of the cube and then just tilt 90 degrees and go into the other side of the cube. On a curved surface, like a sphere or a capsule, the player is obviously going to do this because the angle of the other side of the capsule or the circle as they are moving across it is smoother. They can adjust to it more simply. There is not a lot of difference to the next angle of the geometry the player is going to be stood on, and therefore they can easily transfer from one side of the surface to another side of the surface on a capsule or a circle or even a smoothed plane where there is a tilt to it. Because there is smoothing to the geometry, it's not a harsh angle. The player can move from one piece to another piece very, very simply without any issues of geometry or movement. However, if the angle is too great, as in the cubes that are angled, the player is simply going to ignore the other side of the cube that they would tilt onto, and they are simply going to overshoot the actual surface and be set in the air. So basically, when moving on geometry, if the geometry we are trying to move onto is too harsh of an angular difference from the geometry we are currently on, this geometry value is going to be completely ignored by the system. We don't need to register this as geometry that we're going to move onto. We will ignore this because in regular movement it would be too harsh of an angular directional change and therefore cause too many errors, too many issues in movement. Next, you're probably saying, well, hey Slugglove, you big dumb idiot, how do you handle collision if there isn't any actual physics? And for that I will say, the robo is allowed to clip into walls if she wants to. She's very special. I love her very, very much. Clipping is obviously a very, very big issue. If you are handling movement mechanics at high speeds, it's going to be an issue if you're using rigid body, if you're using character controller, if you're using any setup of a controller, because high speeds do not like going into objects. The core reason a lot of actual physics calculations and movement controllers just have you clip into objects at high speeds is pretty simple and pretty easily fixable, actually. The reason for this is usually because the movement in one frame would overshoot whatever you're clipping into, and you're moving at too fast of a speed to really account for any objects that would be collision in the scene. At least in this instance, I just coded collision in the same way that Mario 64 would handle this sort of thing, or at least my knowledge of such a thing from the speedrun videos I have seen. Essentially what we're going to do is we're going to have our character controller, we're going to have a collision object that they would be able to clip into. The reason they would be able to clip into this is very obviously because they would move completely through this object within one frame because they move at such a high speed. Basically the way collision works is we move character, we move one frame, we move them however much they would move within one frame in their direction. If they would completely walk through an object, then there's no collision happening because they have moved completely through this object in one frame because they are moving so incredibly quickly. At a low speed of maybe 20, 50, this doesn't really occur. At speeds at 500, this is going to be pretty constant and a pretty big issue. So the way I solve this problem is incredibly simple. We take the character. Before we are going to move the character, we are going to say a variety of recasts in the direction they are going to move. We're going to check for any collision in that direction. We're going to check the angle and actual geometry of these collisions. For example, if there is a actual slope angle or the angle of collision is not very similar to the angle of movement. For example, if we are going to hit a wall, but the wall is angled in such a way that it is so harsh of an angle we're basically running alongside of the wall, we're going to ignore all of those collisions because these are collisions that aren't going to cause clipping and more commonly are just going to interfere with the actual movement mechanics. So, no clipping here, baby! What we're looking for is we're looking for flat surfaces, we're looking for angles that are very similar with our movement angle and our player angle, angles that we are going to, in a normal circumstance, run straight into, like a big brick wall. What we're going to do with these is we're going to check the actual collision data of where these points are, we're going to average these out, and then we're going to check how much the player would have moved within one frame. If the position the player would have moved within one frame is going to exceed these clipping points that we have found, and it almost assuredly is because we're only checking the direction and distance that we would have travelled within one frame. We're simply going to check our movement value that we would have travelled in one frame. We're going to reduce this in the direction opposite to itself and by the value of how much we would have clipped into the wall. So let's say we were going to travel a unit of 10 units in one frame. At the collision check, after 3 units, we detect that there is a collision. What we're going to do is we're going to take the value we are going to move within one frame, we're going to reduce this by 7 units, so we're only going to move 3 units, because at 3 units we would have clipped into something. So we're just limiting the movement before clipping even happens to just remove the clipping issue before the player ever actually clipped. It's like thought crimes. You just stop the thing from happening before it even happens because the thing was trying to make it happen. Basically, the way I avoid clipping in this controller is by making it so clipping is an impossibility because the player is not even allowed to move into a position where they would be clipping. Now this has some errors. For example, the player is technically never allowed to touch anything, which is sad. But realistically, this game idea is very low poly, and if the player can never actually touch anything in a wall, it doesn't really matter because they have a big old hitbox, and you're not going to be able to tell that there is maybe a 0.005 point distance between the actual collider and the wall, because the collider is invisible anyway. Realistically, this is the best solution I have found to avoid clipping in a lot of these fast-paced scenarios. The only real issue with this is maybe at a speed value of 50,000, the player will actually be moving backwards because they have clipped through a wall through such a incredibly large degree, but this is the kind of thing in testing where it can technically happen, but these values of speed are an impossibility. So, realistically, there's no actual issue with this system. Next we have in-air movement. In-air movement is very, very simple. Instead of organizing and moving on a plane that we are using with geometry, all we're going to do is move left or right or forward or back in world space, and then we're going to move up or down by an amount set by the player's motor gravity. This is an independent value that I set in the scripting, and it just controls how much gravity should be applied to this character. In the example here, I have the gravity set to 25. When we are set in the air, our gravity is going to be set to wherever our momentum upwards or downwards is. This is done by calculating our vector 2 of momentum with the actual direction the player would be going in. So if the direction would actually carry our player upwards, the y value will be set to the gravity amount. This value is going to be decreased over time to become the actual float value in our script to whatever gravity is, and then the player, when in air, is going to move up or down based on this gravity amount. Once the player detects ground below them, they'll be set on the ground again. This is just done with our basic floor collision checks to see if there is floor beneath the player. Now we'll talk about each individual movement mechanic that the player can perform, going from the most basic ones to the more complicated ones. The first of these is jumping. Jumping is very obvious and simple. There are two kinds of jump, a regular jump and a long jump. A long jump will make you go further forward but have less height added to it, and this happens automatically when jumping at high speeds. All that really happens during a jump is we're set in the air, we have our momentum altered, we have our gravity altered, which is an independent value in the motor scripting, and then we just use our in-air function. The only complexity to this is that sometimes the angle of movement may affect our jump. For example, if we are running up a slope, we're angling upwards with our movement anyway, and we jump, I'm going to make it so that the player has additional height added to their jump based on their direction of movement if they are moving upwards. So basically, if we're running up a wall or up a slope and we jump, we'll have extra height added to our jump to make sense for the mobility that we are engaging in when going up a slope. I decided not to do the same thing for if we are running down a slope. So if we were running down a slope and we jump, we would have our height minused. I chose to ignore the amount that would be decreasing the jump height in this state because it would be unsatisfying for the player to jump when going down a slope and then have their height of their jump be 0 or even a negative amount because they are running down a slope. It didn't really have a whole lot of positive feedback for the player. It made jumping unsatisfying if you're on a slope, and overall is not the kind of movement the player would want when moving in the game. If you're jumping, you're probably wanting to go up, so even if the physics or logic of the systems would make it so that you would jump downwards, I'm going to ignore this in these states because that wouldn't be interesting or fun to do. Next we have the dash mechanic. The dash mechanic is pretty simple. We find the player's input direction. This is done very easily by what input the player is pressing. We will then find the direction that the player should move when dashing based on this input. If the player isn't not pressing any inputs, we're just going to dash in the direction that the player last pressed, which is going to be the forward direction of the robot. When dashing, we're going to add a amount to the player's speed and also their boosted speed, which is a different speed value but is basically the same as regular speed. This is going to make the player go a lot faster than they currently are. We're then going to compare the direction they were going to dash in with the direction they are currently going in with their momentum. So if they dashed in the current direction of the momentum, nothing is going to happen. Their dashed speed is going to add on to their regular speed. They're going to be boosted forward. If they dashed in the opposite direction of their momentum, their dash speed is going to be altered and decreased by the degree that the momentum was going in the other direction, but we're still going to limit it so the dash at least is going to go at the amount of its basic speed. So for example, if we're moving 30 units to the left, we want to dash to the right, we're going to be dashing 30 units to the left minus 6 units to the right. For example, this is still going to be 24 units to the left, so in this instance we're going to completely limit this amount and we're going to default to 6 units to the right. Even though mathematically they would have still moved to the left, we're just going to ignore this completely because I want the dash to have more directional control. However, if the player is moving 30 units to the left and they dash, this is just going to add on to their regular movement, so we're going to get to 36 movements directions to the left. Then just when dashing, we will have different animations play for dashing. We will have a different rotational speed, meaning the player cannot rotate as quickly when dashing, and we're going to make it so the player has different deceleration values, acceleration values, and control values when dashing. All these are very, very simple. Acceleration and deceleration control how fast the player accelerates and decelerates. Control dictates how much the player can move to different velocity amounts, and turn speed dictates how easily the character can turn. All these are also during most movement states, and they are all very, very simple values. The player can dash both on the ground and in the air. The only difference is when dashing in the air, we're going to limit the amount of gravity the player is applied when dashing, and we're going to reduce the actual gravity the player is enacting on. So if the player has been falling for a while and then they air dash, their gravity amount will be set to 0 once again, meaning they will stop their fall and fall again once the dash has completed. Next we have the double jump. Big fan of this one. The double jump, very simple, it's just a jump in midair. It has the exact same functionality as a regular jump. I just changed the movement values for this. The complexity with the double jump is that you can transition into a hover mechanic. This is done, again, very simply. The actual double jump time is half a second. If you hold the jump input for 0.4 of those seconds, it will transition into a hover state instead of a normal state once the player has double jumped. The actual double jump itself is pretty simple. It is just a flipping animation which transitions into a falling animation, and then the gravity amount when double jumping is 0.75 the regular gravity amount, so double jump has a lighter amount of falling to it. It will also slow the player very, very slightly, so double jumping is an option to gain more height or more jump distance, but it is going to limit the player's speed, but at incredibly high speed values. Oh wow. The main functionality of the double jump is to hold the double jump to transition into a hover state. The hover state is going to slow the player's speed dramatically, it is going to slow the player's turn speed very dramatically, and it is going to transition into a hover animation. This is for the player using their boosters to hover in mid-air instead of falling. We're going to then have a deceleration, so the player will eventually decelerate to no speed at all or a very, very small amount of speed when hovering, and we're going to make it so the player has a lower amount of control when hovering because the player is in this state where they're not trying to control their movements with their body, they're just trying to float and hover for as long as possible. And then gravity is going to be incredibly decreased when hovering, so the player is going to fall incredibly slowly when hovering. If the player lets go of the jump button when hovering, they are going to transition into a normal falling state, so the player can stop hovering at any time. This is mostly just for if one were to overshoot a jump or undershoot a jump and they just want to hover over there, the player has the option to do so at the loss of most of their speed, because the hover is going to slow the player down incredibly. Next we have the slide mechanic. The slide mechanic is actually achieved in a very similar way than the hover mechanic is achieved. When dashing, if the player was to hold the dash input, at the end of the dash they will be set into a slide state. The slide state is very, very fun. The slide state, same as the dash, is going to add movement, and it's going to add speed and a boosted amount to the player. The slide is going to gain an incredibly larger amount of speed when floating, sliding downhill, and is going to lose a lot of speed when sliding uphill. If going on a slope, the slide is going to slide in the direction of the slope. If not, it is going to slide in whatever the normalized direction of velocity is. So if we were already traveling to the right, we're going to slide to the right. If we were traveling to the right and we're going uphill, we're going to change our velocity direction and slide downhill. The slide is very good for geometry where you would not be influenced by a slope, or if you would build speed by a slope. It's a nice way to build a lot of easy speed, but at the same time, if you are trying to do a slide when going uphill, you're going to lose more speed than you gain. Next we have launching and land rolling. These are done in a very similar way. If the player is air dashing and then jumps during an air dash, they will transition into a launch state. This is going to move them forward very dramatically, and it is going to play a different animation and stick them in the launch state. The launch state is sort of the in-air equivalent of the slide functionality, being that it is a way to transition out of a dash functionality and gain a bit more speed. The launch state is going to give the player a large amount of speed, and it is also going to decrease a lot of their control over the player. The only difference with the slide and the launch state is that you can actually change your direction when having the launch state, so you could jump, dash in one direction and then launch in the opposite direction. However, this is going to kill your speed in the same way that dashing in a direction that you are not moving in is also going to kill your speed. The launch state, once again, is very, very simple. You have a bit of in-air gravity added to your player, you have more speed and boost added to your player, and you move slightly differently with acceleration and deceleration values. The interesting part of the launch state is when landing, you will go into the land roll state. This is very similar to the launch state, only on the ground. When you land from being launched, you will go into a rolling animation for a short time, half a second. This is going to add speed to your player, and also you cannot accelerate, decelerate, or change your direction when rolling. This is mostly an animation thing I wanted to add, but making it its own movement state actually made the animation read a lot better, because otherwise you could land from a launch, you would roll, but you could still change your direction of movement or turn the character, and obviously when rolling that doesn't look very good. So making the land roll its own state just made the most sense design wise and was the easiest thing to do. And that is all of the basic movement states. Now let us talk about the complicated movement states, like flying. Now you may be thinking, isn't all of these movement states a bit redundant if the player can simply fly? Yeah, but funny? A lot of the design for the controller is made mostly just to be what is fun and engaging for the player to do, and I do not really pay much attention to what is good game design, because here's a little trick for you, game designers. Funny. So just make what funny and remove whatever sucks later. The actual functionality for when the player will start flying is pretty simple. When using the air dash functionality, you will hold the air dash, and then this will transition into a glide state. The glide state is just what I called flying for some reason, because originally it was meant to more specifically be like Mario 64, where the player glides and doesn't have actual flying momentum, and then I found that boring, so I just made a flying movement instead. But internally it is called gliding. But for you and I, gamers in the know, it is flying. Once flying, when the player is holding the dash button or the start flying button, the right trigger, the player will continue to fly. If you let go of this button, the player will transition back into the in-air state, or if you're on the ground, they will transition into the grounded glide state, which, to make things more complicated, the player can fly on the ground and then has an additional movement mechanic for ground gliding when on the ground. Now that I have discussed the preamble of different movement mechanics, I will now discuss the actual mechanics in the flying mechanic of the robot system. The flying mechanic is deceptively simple in the way that it works, and it is mostly reinforced by the actual visuals and the actual speed that you can get up to, which I think gives a lot of nice feedback to the player when flying, when in actuality flying is very, very, very simple. The first thing when flying is the actual controls. When flying, the controls are different. In regular movement, you move in the direction that you press, so if you move right, you're going to be pressing right. If you want to go forward, you're going to be pressing up, or relative to the camera. The issue with flying is that it has flying controls, so you press down and your character is going to tilt up and fly upwards, you press up, your characters are going to tilt down and go down, or the other way around. You tilt left, your character is going to turn left on their actual movements, and you can press the L and R buttons to roll. This would just be pivoting your character left or right relative to their rotational direction, rolling with their movements. And this is all perfectly fine, but it is very disorienting with the camera. So the first thing I need to do is make the camera rotational, the same value as the player rotation. And this is very, very simple. When we go from regular movement to flying movement, we're going to lerp a value from 0 to 1. This will be called flying lerp, and this will control the direction the flying camera is going to be facing. When at 0, it's got a regular camera rotational direction. At 1, it's the same rotation as the player, so it is following behind the player. This means you can easily perform things like loop-de-loops or rolls or spins when flying very quickly, and the camera will follow along with your player, and you do not have to also adjust with the right stick to make the camera also adjust as you are flying, because that is not good. Then all I have to do is, once the player has finished flying, we're going to take this value down from the flying lerp to its regular lerp function. Our camera is going to go back to its normal rotational values, and it all returns to normal. So the camera returns to normal, the player will return to normal in its glide function, but I'll get onto that. The camera is just going to return to its normal facing value, the new forward direction of the camera being whatever direction it currently was set in when flying, and we can rotate the camera and move the camera as normal. Next, we have the player movement when flying. This is, again, relatively simple relative to what you would imagine a flying controller to be, but has its own complexities. So we're going to start our player by flying. This is going to add a little bit of boost to our player. It is going to immediately rotate their visual pivot in the direction where they should be flying in, which is whatever their movement direction is when dashing in midair. So forward, you're going to go moving forward, backwards, you're going to be moving backwards, and then in this state, we're going to rotate our player over time relative to our input buttons. This is pretty simple. I use a quaternion rotate function, and then if pressing up, we're going to be rotating upwards relative to the characters upwards, right relative to the characters right, right bumper, left bumper, forwards rotates in a circle. Basically, we're just rotating relative to the character's actual rotational value, not any world rotational values. This means we can easily just rotate in a circle, and there isn't any loss of function because we're just rotating relative to the character's actual rotational values already. So you can just spin in a circle, don't have to adjust to any world space geometry. It's just player geometry when rotating with the camera, with the player when flying, because it's just rotating to the character's up or right or forward directions. After this, I have the character moving in their direction of movement. This is, again, very simple. It is derived from the rotational value. We're just going to take the speed value. We're going to move forward relative to that speed value. And that is it when it comes to flying. We rotate based on the inputs. We move forward based on the character's forward direction. That is the absolute simplest version of the flying mechanic that there is in this game. You just move forward in the forward direction, and the complexities in this mechanic come from the visual elements and the way speed is lost and gained when flying. The first and most simplest version of this is the flying falling value that I have set up. This is independent of any speed values, any momentum values. Essentially, the longer we are flying and not at a fast enough speed, we're going to slowly be falling out of the sky. So even if we're moving straight ahead, we're still going to be losing our speed gradually and falling very gradually. So to avoid this, the player has to build speed in some way by dipping, otherwise they're going to eventually fall and land on the ground. The way I actually program this is very simple. I have a value that ticks up from 0 to whatever this value should tick up to, let's say 10. We will add this value to whatever the movement direction is, so forward relative to our speed, down relative to the world space, relative to whatever this value is. And then if the player is gaining speed, we're going to reduce this value by the relative amount that the player is gaining speed. So if the player is gaining a lot of speed, we're going to reduce this value by a lot until it is eventually 0, and this value can tick down again when the player needs it to tick down when they're not gaining speed. Next, we have the way the player actually gains speed. I have two values for this being speed gain, speed loss. This is relative to the directional forward that the player is facing. So facing up, they're going to lose speed because they're flying upwards. Facing down, they're going to gain speed because they're flying downwards. These are on two different graphs that I have made. The loss speed is a curved lerp graph, so it starts out very slow and then gets very steep in the amount of speed you are losing. This is the upwards direction of movement, which is then square rooted by 3, so cubed. And then the speed gain value is the same, but the direction downwards, and then square rooted by 2, so square rooted. This makes a value from 0 to 1 in both values, either going up or down, and I can just use this for a very simple lerp function to gain and lose speed. So the closer we are to absolutely going up or absolutely going down, the closer this value is to 1, the closer we are to middling, the closest value is to 0. We're going to use this as a lerp function, which is a function that derives a number from 0 to 1 based on a value from 0 to 1. Our first value is going to be 0, so no speed is gained. Our second value is going to be whatever the speed gain or loss amount is. So let's say at absolutely going down, we're going to gain 50 speed. So at a value of 1, this is going to be 50. If we're going straight down, it's a value of 1, so we're getting 50 speed. And then this value is just added to our actual speed amount by whatever delta time is, so it is added over time to our actual speed. We're also going to make sure our speed, provided we can gain speed or we're not losing any speed, is maintained at a default value, this being 10, so the player is always going to be having some speed when flying because they are using their boosters and they're still having some level of speed. As long as they're not flying upwards and losing speed, they will eventually reach this value, so long as they don't lose speed in some way, and so long as they don't overshoot this value. If they overshoot this value, there's no point making speed equal this value because they're going faster than this value. Next we have collision for flying. The collision for flying is in 2 degrees, the first being when we can fly on the ground, this being if what we're flying on is flat ground, the second being if we have flown into something, and this is my favourite aspect. The way we check for flat ground is the same way we check for flat ground in every instance. The only issue is we're not going to be checking down relative to world space, we're going to be checking down relative to the player character's downwards direction. The reason for this is because you could fly up a wall and make a cool visual effect. When flying on the ground, it is the exact same way as we would calculate movement when flying in air. The only difference is we're going to limit the amount of speed the player can gain when tilting downwards, and we're also going to make sure that their angle direction is the same as the floor's angular direction. The way we're limiting speed when tilting downwards is very simple, because if you are flying into the floor at a very specific angle, I found you could gain infinite speed and not crash into the floor, which is a problem. So if I limit the speed on regular floor surfaces, the character cannot actually build speed if they want to just fly directly into the floor from the moment before they slam their brain into the floor and die. We're also going to check the angular direction of the player relative to the floor's angular direction. If these are too dissimilar, we're going to be flying in the air again, because the player is no longer actually flying on this floor, they are flying at a weird tilted angle away from the floor. Transitioning back to flying in the air is exactly the same as flying on the ground because it is the same movement function. The only difference is we're just going to not play any visual effects, and we're going to handle collision geometry slightly differently when in the air. Next we have the glide on ground state. This is the state that happens if you are gliding on the ground and then you stop gliding, you enter into the glide on ground state, which is very confusingly named. This is when you're gliding on the ground on the ground. This is if you were gliding on the ground and then stopped gliding. This is mostly like a skidding state. This is highly inspired by the dodge in Nier Automata, where if you dodge and then hold the button, you enter this funny skidding state. Essentially all this state is that you will move around with very little control. You have an animation that is just poses that alert with the momentum of the character, and it's basically the impression of your character stopping flying but still having this incredibly large speed maintained, and they're just skidding around until their speed is reduced to a smaller amount, at which point they will just start moving like normal. The actual functionality for this state is there is none. You can move very fast and you have a funny amount of control, but next is the visual feedback for when the player is actually moving. These are for making the player look like they are moving a whole lot faster, especially when flying, because this is the state where the player is going to be moving faster than when they are on the ground. The first of these is the camera FOV. When the character is moving faster, the FOV becomes larger, and this just gives the impression of the character moving faster. They are further away from the camera has more of an FOV that you can see further of this distance. This is just a very, very simple visual trick to give the impression of the character moving faster. The FOV just pulls out and then goes back to normal when the player is at a normal speed. The next of these is the visual particle effects. There are 2 of these, the first one being the wind whistling by the pyre. So these are just trail particle lines that are created periodically based on your speed, and they will move in world space with the character. So they're going to be moving in the direction of the character's movement, and these are just going to give the impression of little wind particles as the player moves. More of these are created for the faster the player is going, or if the player is not going fast enough, none of these are created, and then these are destroyed periodically once the particle effect has finished. So the faster you go, the more of these are created, the slower you go, the slower these are created, and these just move with the player, give the impression of wind moving with the player. Because the player is moving so fast, they are moving through the wind and it blurs things with the wind. Then another of these is applied if the player is moving at an even faster speed, along with the regular wind particle system. Another one of these is placed on top of the player and is parented to their transform position and rotation, so will move with the character. And this is a wind going in a spiral effect around the front of the player. This is more specifically used for when the player is flying, but since it is tied to player speed, it can also be used when the player is just moving fast regularly. And I think it looks fine in both of these states, so I have no reason to disable it when the player is not flying. What this does is it just makes a particle system of wind going around in a spiral to give an even greater impression of wind resistance and wind that the player is pushing around because they are going so very fast. Next, we have audio effects. In the same way that the FOV is lerped from a lower FOV to a higher FOV, I will also lerp a looping audio effect of wind whistling from a lower wind whistling to a higher wind whistling. These are just going from a audio amount of 0 to 0.5, so the faster you're going, the more you're going to hear the whistling of wind as you're running through the wind and going very, very fast. In old projects, I have tried to put off doing audio effects because I don't like setting up audio effects very much, but they provide such a heavy and detailed amount of feedback to the player that I feel like not adding audio effects to a project until very, very late actually diminishes the quality of the project, because then I don't have this very important feedback and satisfying visual that could actually help in design. Because with this feedback and visual audio that is being created with the wind audio, I feel like it helps to make the actual flying feel a lot better, and means that I wouldn't try to rework the system that is already fine when all it needed is just an audio effect. And then finally, I have the actual boosters animators. These are two different animators. I have a animation override for the player with a boosted animator on their back and on their legs. So when using a booster, these will open up or close with the animator, and these will override the positioning of these bones in other animations, so I can have these on top of any animation I want. And all these do is they open up or close part of the player's body, depending on if they are using a booster or not. And then I have 6 different boosters tied to the player, which will be enabled or disabled when certain animations are playing or certain states are playing. For example, when the player is on the ground moving normally, none of these are going to be enabled, so we're going to have all of these have a speed of 0. The animations are going to be playing at a speed of 0, and their scale is going to be shrunk down to a speed of 0 until it is actually 0, at which case these are all invisible. But if the player is flying, all of these are going to be turned on because I want the impression of the player actually using their boosts and moving at a much faster speed. So I have these all lerp to a speed of 1, the animations are actually going to be playing once again, and I have these all lerp to a size of 1, so it has the impression of the boosts starting up and moving and being used as the player is using each of these functions. These are all 6 different animations or animators that are tied to the player's rigging, but are just different individual objects that I have childed to the player, and then I can enable or disable with the visual scripting that I have set up. Next, I have the dust particle visual. These are low poly little dusts that will be created and then grow over time and then disappear. This is a pretty simple visual effect, and it's just to give the impression of the character moving at such a high speed. They're going so very quickly that they're kicking a lot of dust up when moving. The original reasoning for such a function is because when the player is flying on the ground, this will also create this dust particle effect and give the impression of the character kicking up dust as they're flying so quickly. But I found it so interesting and satisfying that I made the effect still apply if the player is not flying and just running on the ground. The same logic kind of applies. The player is moving on the ground at such a high speed that they're kicking up a lot of dust. The only difference is when running and not flying, this amount is going to be slightly lessened and the dust is going to be smaller and not as intense when flying, but realistically the same visual feedback applies. The player is moving so quickly that they're causing a mini little dust storm as they move. I think this visual, it has a lot of really nice feedback to it, especially if one was to go very, very quickly and then skid and stop somehow, or if they were going very, very quickly in midair and did a jump but then landed without pressing an input, so they're going to stop very quickly. The dust is still going to play because the player is still at a high speed, so it gives a lot of feedback for the player as if they are skidding just from the existence of the dust, when in reality all the player is doing is sliding along in an idle pose. Next, I had the collision information when flying. Similar to the collision information when moving normally, the player has to have collision information to detect if they are moving into an object at a very high speed to avoid clipping. Obviously, this is going to be used when flying. It's just going to be in the direction of flying instead of the direction of momentum, as previously would have been in the other movement systems. But we also have a few other checks. We'll have a check to see if there's anything in front of the player in a certain distance to the player, regardless of momentum, and we'll also have a check for the ground. If we have a check for the ground, this can just switch our flying state from normal to grounded, and then that will work in the exact same way it normally would work with the flying state. It just makes a visual effect when on the ground. Then the check in front of the player is going to delay the character's momentum if they would clip into an object, and also at a certain speed if the player had collided with something in front of them, we're going to stop flying and we're going to go into the knockback state, because this is sort of the version of the player crashing. Essentially, they've driven very quickly into something, and unlike regular movements at such a high speed and also when flying, the most satisfying feedback for the player is to simply make them crash from what they have hit, because having them slow to a stop or have any other kind of movement or bounce off the object would not really feel correct when flying at such a high speed. At this point, you kind of just want the player to bash off something and give the visual of the player actually crashing. Next, I had the knockback and launch states. These are for when crashing when flying, but they will also be implemented when I add combat for the character being launched by enemy attacks. But I haven't done that yet, so the states are just when crashing. When crashing into something, I get the normal direction of whatever the player crashed into. This is going to find the direction to push the player backwards. Once we have crashed into something, we're going to rotate the player backwards in the direction of whatever they crashed into, so they are facing the absolute normal of the wall that they have just crashed into. We're then going to play an animation. This would be the launched animation, which is the player being pushed upwards and backwards, and then spiraling as they fall down. This animation is just a blend animation going from the launched upwards and down into the animation of spinning as they fall. So it's very, very simple to actually implement. The actual movement for the state is very simple. We're going to apply a negative momentum backwards. We're going to kill speed and kill the boosted value because the player is launched and they can't do anything until they land. Once the player has landed, they'll enter the knockback get up state, in which they will have all of their momentum killed. They will have all of their speed and boost killed, again, in case they got some somehow. And we're going to wait for an animation to play until the player can actually get up. The animation is the player lying prone and then getting up and being ready to play once again. It's sort of like a stun state. Once the player has been knocked back, they have to have this feedback of laying on the ground as if they have a struggle to try and get back up, and also because if the player was knocked back and then just landed completely normally, it wouldn't give a lot of good visual feedback for the player actually being stunned by such a state. It would feel like the actual knockback was quite pointless if the player could just normally get up once it is done. And then finally, I have the long fall state. This is very, very simple. If the player has fallen for 30 units, this is being 30 units in world space, then they will enter the long fall state. This can be exited out of by either dashing or double jumping, at which point the height of the long fall will be replaced, and once they fall 30 more units, the player will once again be entered into the long fall state. This has its own animation, which I quite like. It really gives the impression of the player moving very quickly as they are falling very quickly. Gravity is more intense during a long fall state, but it will also leap slower to the actual maximum gravity, but maximum gravity can be a lot more intense when falling. This is the state when the player has been falling for a very long time. After falling, they will enter the knockback get up state, which is pretty much just the same as the knockback get up state. It's just being triggered from a different function and will have a different animation triggered when starting it, but it is essentially the exact same state. The player is stunned for a moment until they get back up. The only difference is the animation is when falling forward, so they land on their face instead of when knockback, where they are falling backwards, landing on their back. Finally, animations. This is the actual reason I even started this project, baby, just to animate. The animations I very much like. The original reasoning for starting this project was exclusively because I wanted to make something that moves really fast, and also because I really wanted to try at 12 frames per second animation. This is animating at 12 frames per second, which is a lot of fun to do and a real bother to import into Unity for its own reasons, but this is just animating at a very slow frame rate. This is incredibly useful for very stylized animations because a lot of animated studios now are doing it in their movies, and it's very good for displaying action that may be complicated in a more readable format and really give a lot of weight to movements and also make animation look more stylized. And also, and here's the real point, it's a lot easier to do. Oh my goodness, it is so easy to animate in 12 frames a second. It still has its difficulties, mind you, but as somebody who animates in 60 frames per second for emotes for a living, it is so much easier to animate something at 12 frames a second. You can very easily go frame by frame to point out errors. It gives a lot of stylized feedback to the actual motions. It is a lot of fun too. Mostly it's just a lot of fun. And if you have never animated in 12 frames per second and you enjoy animation, I highly recommend it. I will not go over every single animation I have made for the project because there's a lot, because I get carried away very easily when animating. But there's some that I really like. I think the running poses and the walking poses are all really good. They have a lot of weight to them, obviously. I try to make the actual impression of the heaviness of the robot very obvious when animating all of these, and I also feel like they needed to have a lot of very fast, snappy movements, which is, again, very easy to do in 12 frames a second. 12 frames a second really aids itself to animating robots because they look naturally more clunky and stylized by default, so animating them in this way just helps a whole lot. Other notable aspects of the animation is that I animated a lot of the animations with poses, these being just static poses that are blended together with blend animations in Unity. These are for obvious reasons. Things like the dashing or gliding in air do not really need to have specific animations for them. It would be nice if they did, but given the stiffness of the character, they don't really need an animation for them, so I just have animations that are poses and then these are blended within Unity. The reason for this is very simple. It's a lot easier to just animate one pose, and it's also a lot better, I feel like, for fluid motions like the glide on ground state. Oh my goodness, I haven't talked about the glide on ground state. I should do that. That's a complicated state. I mean, at this point in the devlog, you've already seen that part, but I haven't. I'm just going to go back and record it. The actual poses give the impression of the actual fluidity of the movement and give a whole lot more feedback to the player as the actual motion that they are performing in-game, because the animation directly is caused by the in-game animation, by the in-game motion. And that's it for devlog. I don't think you've watched this far, if I'm being perfectly honest with you. 55 minutes into a devlog about me rambling about flying controls? No, you didn't. You're a goofball. Don't kid me. This has been a very fun project to work on. This is actually just a project I'm working on for fun while I'm doing other projects, because in a freelance project I was working on a third-person controller, and that made me very much want to make a third-person controller about very fast movements, and it made me make this controller in my free time, which, between you and I, is about 20 minutes a day. Hi, I have a lot of irons in the fire. I'm burning the candle at both ends. I like coding so much. This has been a fun project to work on. It is, as I mentioned, a thing that I have had thinking about while working on other projects, just thinking, coding a different project, thinking, what if I made it very fast, though? Wouldn't that be a real hoot? So this has been my fulfillment of making a very fast controller. Realistically, it's something I wanted to be doing for a long time while working on Pet Pal, because Pet Pal is a very fast, momentum-based 2D game. I've always been feeling like it would be enjoyable to try and do a similar thing in 3D, and then I ended up making it a whole lot faster than I had intended to, just because that is more entertaining for me. If you have watched previous devlogs by Little Me, Little Sliglove, you will probably notice an overlap in different mechanics. For example, the flying mechanic is very similar to the third-person flying controller that I had made as some of my earlier videos, bad ones. The actual sliding grounded glide function, the one that is floaty around, is very similar to the dodge mechanic I made in a previous action game. The walking on curved surfaces or complicated surfaces without use of physics is very similar to two different game projects, one being the stunning controller, one being the other third-person action game, the one with the blue girl with the horn. Remember that one? Wasn't that one fun? Essentially, this is a culmination of a lot of different projects and different things that I have made in previous devlogs and previous projects and other things that I have been doing because I spiral around the same project over and over and keep remaking what I have already done in a Sisyphean task of perfection that I will never reach. But one day, if I'm very lucky, the boulder will roll on top of me and squish me into a funny little pancake, and that'll be nice. Will I ever finish this game? I'll never tell, but other mechanics I have planned for this game are mostly for it to be very action game focused, which may come as a shock to you given the very, very complicated movement system and also the fast-paced movement system. I have, again, a very big fascination with fast-paced movement systems, but I also have a very big fascination with action games because I play a lot of them. And making this game function has made me feel or think about what if an action game could also be incredibly fast-paced to the extent that this game is fast-paced. How would that actually work? My just thoughts on the design process right now that I am saying in the rambling end section of the devlog that nobody's listening to. We're all alone here. That my thought of this is mostly that it would end up being similar to a dogfighting system or a Star Fox game where combat is very fast-paced because you're flying around, but has some level of adjustments and ease to it that makes it so that actually committing to combat at such a high speed isn't ridiculously impossible to do. Or another solution I have had is that maybe the combat in this game would be more horde-based, more hack-and-slash based, and there is a whole lot of adjustment or easing of the character because the character is larger or more combatly oppressive than the enemies, and therefore the insane speeds that you can reach the game are not a detriment to the actual combat of the game. Sort of like a EDF game or a Warframe where your character is like a knife through butter, which is a fun idiom, meaning that they can cut through enemies very easily. Also, while we're here, in the void, let's talk about different mechanics I have already added. I've already added a parrying system and a system to parry projectiles because I wanted to do that, and it's very satisfying and what the next robot devlog will be about. I am very much losing my voice at this point. I've been talking for too long. But after this, I would very much like to work on the combat system, specifically the way combos and attack strings are handled. My idea for this is to have a set of attack strings tied to whatever weapon is on your left or right arm, and then the direction will correspond to different attacks that you can have with this weapon. So forward direction on the right arm could be a light attack, backwards could be a launcher, left could be directional, right could be something else, and then each of these would have 3, so there'd be 3 forwards, 3 backs, 3 left, 3 right, and then you could string these together with the other attacks on these arms and the other attacks on your alternate arm, meaning that combat would have an ability to be very complex while also being very, very simple because it is just 2 buttons and a directional stick, and combos are all the same, just 3 buttons in whatever order you want the combo to be, which I feel like would aid the actual design of this game a whole lot. It's been an hour, so let's end it here. Let me know in the comments what you've learnt from Little Slug Glove. Aside from, of course, how autism causes obsessive tendencies, because I feel like this video has outlined that pretty well. What have you learnt about robots? What is your favourite Gundam? How many Gunplas do you own? How many Gunplas do I own, you ask? Not enough.